Hi and welcome to Maths class. So in our last video we looked at discrete random variables, and one of the things about those is there's lots of different types of discrete random variables. So what we need to be able to do is identify the type that we've got, and then we find out what the distribution is that goes with it. So the first one we're looking at the moment is called a Bernoulli sequence, which leads to a binomial distribution. So a Bernoulli sequence is quite easy to recognize, but it's really important that you take that step at the beginning of looking and thinking, is this a Bernoulli sequence? So it's an example of repeated trials which result in either a success or a failure. So if you're looking to try something like throw a ball in a hoop, you will either succeed or you will not succeed. Now, of course, the word success and failure has implications for us of good and bad, but that's not always the case. So anything where there are two distinct outcomes where you could call one success and one failure would be an example of this. Okay, so once we've worked out that we've got a Bernoulli sequence, then we look at the probability of success and we call that P. And therefore the probability of failure we call Q, and that's always 1 minus P. So if I know that the probability of success of my throwing a ball in a hoop from a certain point is maybe 1 on 10, then P equals 1 on 10 and Q equals 9 on 10. That's my probability of failure in any one trial, okay? But a Bernoulli sequence, of course, we're no longer dealing with single outcomes, single events now. We're dealing with a series of outcomes and calculating, well, for example, how many balls might I expect to get in the hoop if I tried it 10 times. So one of the other important things for a Bernoulli sequence is that trials are independent. The outcome of a trial doesn't change the probability the next time I go in for a trial. So some simple examples would be repeatedly flipping a coin, and then you note down each time you get heads. You might stand on a fixed spot and try and kick a goal with a probability of 1/4 of kicking a goal each time. You might pick out a card out of a pack and note whether or not the card is a heart, and then return each card before picking a new card. So notice that in this example, there's no way you could really call hearts a success and not a heart a failure, unless you're playing a game where you need hearts. It's just a case of there is one outcome and there is the complement of that outcome, or not getting a heart. In the last one, for example, it's known that 6% of items on a production line are faulty. I select one and I note if it is faulty, and then I repeat this at random times throughout the day. That's just another example of a Bernoulli sequence. Okay, so now, what is a binomial probability distribution? Once we've identified that we've got a Bernoulli sequence, then the number of successes in n trials of a Bernoulli sequence is called a binomial random variable, and it has a binomial probability distribution. And we'll learn there's a formula for it, basically. So what the key here is, we learn to identify that we've got a Bernoulli sequence. That tells us we can apply the binomial probability distribution formulas, etc. Okay. So we're going to look at this example, and by looking at this example, that'll help us to get a better understanding of binomial distribution. So here's my example. We are playing a dice game and I get a point every time I roll a 5, and I have 3 turns. Okay, I get a point every time I roll a 5. I have 3 turns. Rolling a 5 will be a success and rolling anything else will be a failure. So the first thing I can jot down here is that I know the value of P is going to be 1/6, because the probability of getting a point is 1/6. And Q is 5/6, because the probability of not getting a point is 5/6. Okay, then the next thing that I need is to define my variable. So I'm saying let the random variable X be the number of successes in 3 trials. So that's what I'm counting, is the number of successes out of 3 trials. So there are 4 things that can happen. I can have no successes and end up with no points. I can get, out of 3 rolls, I could get 1 5, I could get 2 5s, or I could get 3 5s. So let's look at the probabilities of all those things. So first of all, the probability of having no 5s. It's quite simply going to be 5/6, that's getting not a 5 the first time, times not a 5 the second time, that's 5/6 again, failure the third time, 5/6. So I end up with 5/6 cubed, which is 125 over 216. Okay, let's look at the probability of getting 1. This is a little bit more complicated because I could get a 5 the first time, or the second time, or the third time. So if I get a 5 the first time, it will look like this. 1/6 times 5/6 times 5/6. The 1/6 for getting the 5, and then the 5/6 because the second toss of the dice, I didn't get a 5, and then the third roll of the dice, I didn't get a 5. So 1/6 times 5/6 times 5/6. But what if I got the 5 the second time? So I have to also include that possibility. So that's going to give me 5/6 times 1/6 times 5/6, which is basically the same, right? They're just rearranged. And then, of course, if I get a 5 the third time, but not the first 2 times, it's going to be 5/6 times 5/6 times 1/6. So this is the same number 3 times. Obviously, what I've got here is 3 lots of 1/6 times 5/6 squared. Okay? All right. What about the probability of getting 2? Oh, I didn't say what that equals. That's going to be 25 over 2 times 36, 72. Okay, the probability of getting 2 is going to be something similar, but this time I only don't get a 5 1 out of 3 times. So maybe I don't get a 5 the first time, which means I get 5/6 times 1/6 times 1/6. Or maybe I don't get a 5 the second time, so I get a 5, and then I don't get a 5, probability of that is 5/6, and then I get a 5, probability of that is 1/6. Or maybe it's the last time I get a 5, yay! I roll again, I get a 5, yay! I roll again, don't get a 5. Can you guys see that? Not quite, let me just shift it. Oh, not quite, well and truly not. I'm going to shift me as well. Hang on. Okay, that'll do for now. Let's keep going. All right, the last one. Oh no, I haven't collected this yet. So this is again the same number 3 times. This is the same as this, is the same as this. The order is just different. I've got 3 lots of 1/6 squared this time and 5/6 just once this time. So hopefully you're starting to see a pattern now. In this one, my 5/6 was cubed. Here it's squared, and here it's to the power of 1. In this one, my 1/6 was to the power of 0, which gives me 1. Here it's to the power of 1. Here it's squared, okay? And then when I look at the coefficients, I've got 1 and 3 and 3. So if you've already recognised the pattern, and you can probably already guess what the next term in this sequence is going to be, but let's just calculate what I get here. This is going to end up with 5 over 72, and then finally the probability of getting 3 points is going to be, I'm going to roll 3 5s, so it's going to be 1/6 cubed, which is 1 over 216. Okay, so the pattern is definitely there. This is now 1/6 cubed. So the probability of P starts with a power of 0, then it's got a power of 1, then it's got a power of 2, then it's got a power of 3. The probability of Q starts with a power of 3, then goes to a power of 2, power of 1, and a power of 0. And my coefficients are 1, 3, 3, and 1, which also might look familiar to you. We're going to get onto the formula shortly, but first I'm going to graph this. So let's have a look at what this looks like when I make a graph. Oh, I haven't done that. Hang on a sec. So in order to graph it, I've just quickly jotted down the approximate values just to help me get a feel for their size. And then I've just popped those into the graph here. So we can see that the probability that x is 0 is the tallest by far. It's really quite likely that I'm going to get no points. The probability that I'm going to get 1 point is a bit more than a third. The probability I'm going to get 2 points is less than a tenth. And the probability I'm going to get 3 points is practically nothing. Okay, but let's look now at the pattern that we've just explored. So here you can see the pattern from the game that we were just looking at. The probability of obtaining x5s in this game, where there are 4 possible numbers that we can get for x. There's 0, 1, 2, or 3. This is the formula for how we can calculate this. Now the 1/6, let's look at this. The probability that x equals 0 is going to be, well, when x is 0, I get 3, 0. And that, of course, is this. All right, that's the same notation. And I haven't done that revision with you guys. I'll do that in just a sec. Multiplied by 1/6 to the power of 0, multiplied by 5/6 to the power of 3 minus x, so that's 3 minus 0. And that is exactly what we got, where this, in this case, is equal to 1 times 5/6 cubed. And I can do the same for each of these, and this is going to give me my pattern that I looked at before. So let's just quickly revise what we've got here. So I've just dropped that formula in for you. NCR, which we used to call sometimes N choose R, can also be written in this bracket formation. And it's calculated by n factorial divided by r factorial over n minus r factorial. Now, that's a little bit complicated, but try and remember also this, is that if I start to follow this pattern, I actually use Pascal's triangle. So Pascal's triangle starts with a 1, a 1, and a 1, and then I just add the rows. So 1 plus nothing gives me 1, 1 plus 1 gives me 2, 1 plus nothing gives me 1. Keep adding, put a 1 on the outside, 1 and 2 gives me 3, 3, and 1. And that's the pattern that I've got here, because it's my 4th row, and I've got 4 outcomes here. All right, my next row would look like this: 1, 4, 6, 4, 1. And my next row would be 1, 5, 10, 10, 5, 1. This can be a quicker way than going via this to try and work out what your coefficient is. Use Pascal's triangle, and then however many you've got here, that's the row you've got up to. I'm up to the 4th row, so I needed the row with 4 items in it. Okay. All right, so let's look at that in general. This is specific to the game we just played. Here is what it looks like in general. So in general, if capital X has a binomial distribution, and we know it's binomial because we've identified it's a Bernoulli sequence, then the first thing we write is X is binomial. That little squiggle means it's binomial. The B means binomial. And then the first thing we put is N. N is the number of trials. And the second thing we write down is P. Quite often, there's a mark in writing that down. Now, you don't have to do it in that notation. You can write X is binomial, N equals whatever the number is, P equals whatever the number is. But in the game I've just played, I would have defined X as the number of 5s out of 3 trials, and then I would have written X is binomial, 3 trials, probability of success is 1/6. Okay, just jot it down. there's a mark in it 9 times out of 10. All right, don't forget that step, because just as there's a mark in it, if that's all you can do, even if you get the right answer, if you haven't written this down, you might miss a mark. So make sure you write this step. And then this is the formula. The probability that x equals small x, which are the individual numbers, is this combinatorics here, p to the power of x and q to the power of n minus x, where x is any number from 0 to n, and we start at 0, and then there are n trials. Okay, so n is the number of trials, p is the probability of success, and q is the probability of failure in each individual trial. So let's do a couple of examples. The first one is fairly simple, and the second one's only a little bit more complicated. So here I've got 72% of union members are in favour of a certain change to their conditions of employment. A random sample of 5 members is taken. So it's a random sample. That's pretty important. And 5 tells me that there's going to be 5 trials. Okay, each time I randomly pick a person, that's 1 trial. 72% of union members are in favour. So let x, hang on a sec. So I've just defined my variable. Let x be the number of union members in favour of this change out of a sample of 5. And the other thing I'm going to straight away jot down then is that x is a binomial distribution, where with a sample of 5, there are 5 trials, and the probability of success, that is a union member being in favour, is 0.72. I never write a percentage, I always write it as a number between 0 and 1. Okay, so now we can start answering questions. What is the probability that 3 members are in favour? This is asking me for the probability that x is 3. So I'm going to use the formula. So in order to do that, let's first jot down the formula here. Okay, there's my formula. So now I can use it. I want the probability that x equals 3. So that's going to be n is 5. So it's 5. Choose x is 3. P is 0.72 to the power of x, and x in this case is 3, and multiply that by q, which is going to be 1 minus p. So in this case, that's going to be 0.28 to the power of n minus x, which is 5 minus 3, so that's 2. So notice that these 2 powers will always add up to n, right? That's this number here, n. Those 2 powers will always add up to n. And then the easiest thing to do now is grab my CAS calculator and put that straight in. So that's what I'm going to do. So here is what that looks like, and I wasn't sure if you would know where to find these guys in your CAS calculator. So there he is, and this is in our catalogue, and then you go down to advance when you want to get there. So I put that straight in, even though I could have gone straight to my Pascal's triangle to work out what that is. But I knew I had to do all this stuff anyway, which I wasn't going to do by hand. 0.72 to the power of 3, 0.28 squared, and it gives me 0.2926. So let's go to 4 decimal places. 0.2926. Oh, I'm still in red. Hang on. Okay, that's A. 3 members are in favour of the change in conditions. Okay, B's a little bit more complicated. I need at least 3 members in favour of the changed conditions. So that basically means I'm going to want the probability that x equals 3 plus the probability, well actually, let's jot that down. Probability that x is greater than or equal to 3. That's what I need. That's my proper notation for that. And it does mean probability x equals 3 plus probability x equals 4 plus the probability that x equals 5. So what I'm going to do is I'm going to put all of this straight into my CAS. I'm not going to write, oh, maybe I better do it for you. Yeah, let's write it all down. We already know this one, 0.2926, although I'm not going to use the rounded number in my calculation. I've still got that saved in my calculator. I will just add the other two. And then I have, this is 5 choose 4, which is going to give me a value of 5. Then I'm going to have 0.72. Now this is to the power of x, and x is 4. And then it's going to be times 0.28. And then plus, not times, plus, it's going to be 5 choose 5, which always returns me a value of 1. Times 0.72 cubed. I'm not going to write times 0.28 to the power of 0. Okay, so that's what I'm going to put into my CAS calculator, and let's go and have a look at that. So I jotted that into my CAS. You can't really see the whole thing, but I've got, I've just copied that down, and then I've simply changed the 3 to a 4, and I've gotten rid of the power of 2 in the second one and changed that to a 4. And in the third one, I just went plus 0.72 to the power of 5. And so I've got my answer 0.8624, if I round it correctly. So 0.8624, let's put that in. Okay. So let's recap what I've done. First, I read the question and identified it as a Bernoulli sequence because I know how many samples will be taken. There'll be 5. And each sample, each individual member that's selected has only 2 distinct possibilities. Either they're in favour or they're not of these certain conditions. So it's definitely Bernoulli, which means I can use a binomial distribution. And so then I defined my random variable, which I always have to do. I noted the key information about the question, that it is a binomial distribution, that n is 5 and that p is 0.72. Then I proceeded to use the formula to answer the questions. Okay, there is one more worked example to look at, so let's go to that now. And this one is slightly different. A darts player knows that the probability of scoring a bullseye on any one throw is 0.3. And we need to answer to 4 decimal places. So the player takes 6 shots. Firstly, find the probability of missing each time. And then secondly, the probability of 4 bullseyes, given that he scores at least once. Now that first part is very similar to the previous question. So my suggestion to you would be to pause now and attempt part A, and then come back and just check your answers against mine. But part B is going to be a little bit different. I need to find the number of throws required to ensure a probability of at least 0.8 of scoring 1 bullseye. So now I know the probability, but what I don't know is the number of trials. So it's still a Bernoulli sequence, but it's going to be a different one to solve. So let's start with the easy part, which is part A. And I'm going to use my formula. And so the first thing I need to do is define my random variable. So I'll do that, not on your time. Okay, so I've defined my variable. Let x be the number of bullseyes after 6 shots. Then x is binomially distributed with n is 6 and p equals 0.3. I've put down the important information and got myself at least 1 mark. So now the probability that x equals 0 is what I'm asked to calculate in part 1. The probability of missing each time, that means I get no bullseyes. So it's going to be, x is 0, so it's going to be n and x here. So n is 6 and x is 0. And then it's going to be times p to the power of x. Oops, I don't want to write down p. P to the power of x, which is 0. And then it's going to be 0.7 to the power of n minus x. N is 6 and x is 0. So this is to the power of 6. Now, I didn't really need to do that in order to answer this question, and sometimes it's a useful thing to stop and think, is this making sense to me? if I miss each time, I'm basically going to go 0.7 times 0.7 times 0.7 times 0.7, and that's what this formula is going to give me. So I'm going to pause while I go and plug that into my calculator, and I get 0.117649, but I'm asked to go to 4 decimal places, so 0.1176. Okay, part A, so far so good. The second part, the probability of 4 bullseyes, given that he scores at least once. So this is a conditional probability question, so I have to make sure that I treat it in the same way. So first of all, let's jot down exactly what I'm asked for here. The probability that x equals 4, given that x is greater than or equal to 1. So let's now remember what I said about conditional probability. Don't skip any of your working out. Show every step because there's marks in it, okay? It's not the only reason though. If you show every step, you're much less likely to make mistakes. That's the real reason why there are marks in it. Okay, so that means we want the intersection, this line of working is required, the intersection of x equals 4 and x is greater than or equal to 1 over the probability that x is greater than or equal to 1. And that can be found, well, the intersection of x being 4 and x being bigger than 1 is just x being 4. So I'm going to have to calculate the probability that x is 4. And on the denominator, the probability that x is greater than or equal to 1, the easiest way to do that is going to be 1 minus the probability that x equals 0 plus the probability that x equals 1. Sorry, I can't read that. Can you guys see that? Not quite. Let's shift it. I might just make it a tiny bit smaller. Yeah, you can still read that, can't you? Okay. So that's my fraction that I need. So I'm going to write, now when I say show full working, I want to show this line. I've got to show this line as well. So this is the line where I simplify my intersection. You've got to show what you get out of this numerator here. So now the probability that x equals 4 is going to be n is 6 and x is 4 times 0.3 to the power of 4 times 0.7 to the power of 6 minus 4. And that's all over 1 minus, I've already calculated the probability that x equals 0, 0.117649. I'm not rounding it at this stage, I want the whole thing, but that is an exact value. There were no more decimal places. And then here I'm going to have 6 choose 5, which is 6 times 0.3 to the power of 5 times no, that's not correct. It's going to be 0.3 to the power of 1 times 0.7 to the power of 5. Now what I'm going to do is go away and I am going to put this all into my calculator. Okay, let's see if I can show you that. So that's what that looks like in my calculator. What you can see there is that I've got the 6 choose 4 times 0.3 to the power of 4 times 0.7 squared, and then on my denominator I've gone 1 minus the answer that was still in my calculator, so I didn't delete it, it was still there. And then I've added the 6 times 0.3 times 0.7 to the power of 5. Okay, all done. I'm going to go to 4 decimal places, so the answer that I will write down is 0.1027. So let's do that. 0.1027. So all my working is here. It's a little bit squished up because I was running out of space, but all my working is here and my answer is here. All right. It's not advisable to start jotting down 4 decimal place approximations and then put that into your calculator at the end. You're better off just keeping everything and coming out with your final answer. Okay, that was part B. The probability that I'm going to get 4 bullseyes given that I get at least 1. Now, actually for part B, we're going to come back and look at part B later because it actually is related to exercise 14C. So I'm not going to do that now, and anyway, this is long enough. So I'll leave you with that and we'll return to example 2 part B in another video.